What color is the ocean? Trick question, it's all kinds of colors. Blues, greens, reds, yellows, and swirls of all of the above. And these colors can tell us a lot about what's going on just beneath the surface, what's thriving, or changing, or could pose a threat. For over 20 years, NASA has been looking at the color of the ocean with technology that's, well, over 20 years old. And that has told us a lot about the health of ocean ecosystems, but there are details we just can't see. Enter PACE, the Plankton Aerosol Cloud Ocean Ecosystem Mission. PACE's new instruments will look at our world's oceans, lakes, and rivers in an entire rainbow's worth of color and beyond, giving us new insights into marine communities, the carbon cycle, and climate studies. So let's take a look at the top 5 official best ever ocean colors of all time. This is the open ocean. Here, the oceans absorb the longer red wavelengths and scatters the blues. In these vast stretches of deepest blues is where the tiniest of bacteria cycle and recycle nutrients in microbial loops. For example, the tiniest and most abundant photosynthetic organism, Prochlorococcus, converts carbon dioxide into organic compounds and forms the base of the marine food web. These phytoplankton are eaten by tiny zooplankton, and then eaten by larger zooplankton, then smaller fish, and so on. And then return the nutrients back through respiration and remineralization, which are then taken up by the tiny microbes. But here is where things are changing. These deep blues are getting greener with a warming climate, but exactly how and why is unclear. Despite some scientific theories, the past and present satellite sensors just don't have enough sensitivity to color to tease that out. PACE will fill in those gaps with higher spectral information and slowly, over time, be able to discern the drivers associated with these detected changes. This appealing brownish orange is the result of what's known as colored dissolved organic matter. We can think of it as a kind of tea that leaches out of dead or dying organic matter, like the tannins from broken down leaves, giving the surrounding water a darker, browner hue. Found in higher concentrations in lakes, rivers, estuaries, and marshes, colored dissolved organic matter is a great proxy for dissolved organic carbon, a big pool of carbon in aquatic systems, and it's an indicator of the health of an ecosystem. Much like a cloudy cup of tea, higher levels of this organic matter don't let as much light through, changing the availability of light for plant-like organisms in the environment. With PACE's ocean color instruments' hyperspectral measurements, even into the ultraviolet wavelengths, we'll be able to differentiate sources of this organic matter and better understand the transfer of carbon across land and into coastal regions. A grayish green in a large lake like this could spell potential harm from a bloom of blue-green algae known as cyanobacteria. Depending on the type and abundance, cyanobacteria can spread toxins to aquatic and human life. In 2019, Lake Erie saw a bloom of the Microcystis cyanobacteria form a thick layer of scum filled with a toxin, which posed a major risk to drinkable water. The microcystin toxin can cause liver damage, dizziness, numbness, and vomiting. Researchers are eager to use the hyperspectral information from PACE in order to detect early stages of harmful algal blooms like the ones in Lake Erie. PACE will be able to measure the unique optical properties of cyanobacteria, which will help separate the harmful algae from other phytoplankton present in the water and allow resource managers to monitor the health of fresh water. This turquoise stretch tells us a lot about the sediment churning in the water, and both the quality and quantity of that sediment can have big impacts on marine life. For example, in Greenland, glaciers can bulldoze over surface rocks, grinding them into a fine powder of silt and clay known as glacial flour. The glacial flour changes the appearance of the water, with the particles absorbing the shorter wavelengths, purples and indigos, and the water absorbing the longer wavelengths, the reds and oranges. This sediment can bring nutrients and fuel algal blooms. But if you're an oyster, sediments could be a big problem. When lots of sediment is suspended in the water, filter feeders like oysters can't feed as efficiently. And high sediment levels can be associated with increased harmful Vibrio bacteria, which can cause sickness and even death when those oysters are eaten. PACE's hyperspectral measurements will see far more variability in reflectance and give us better estimates of water clarity and particle size. And that data could be used by oyster farmers monitoring the health of the shellfish population. As the days grow longer in the subpolar regions, a milky, swirly light blue hue grows in the oceans. This is the telltale mark of coccolithophores. Coccolithophores? Coccolithophores. A kind of phytoplankton that is completely covered in a chalky shell of calcium carbonate. When these plankton bloom and then die off, that inorganic chalky material sinks to the ocean floor. PACE will better observe these particular blooms, allowing researchers to account for the amount of carbon coccolithophores remove from the atmosphere and sink into the depths of the ocean. If all of these colors can tell us what's going on with our ecosystems, our health, our climate, then PACE's enhanced resolution is going to reveal new levels of detail in how humans and water are connected in a changing world.